Hello everybody, welcome back to Conceptual Physics. So we're talking about vector scalars, and the reason why we talk about that is so we can talk about projectiles. Okay, so projectiles. So the definition is that a projectile is any object that moves through the air or through space, acted on only by gravity and air resistance, if there is any. So what is a projectile and what isn't? Well, if we have a hill and we have a ball rolling down the hill, is that a projectile? No, not at all, because it's not moving through air or space only, it's also touching and moving off that on that ramp. Now let's say it gets to the end of the ramp. Right at that point, that is now a projectile, because no longer is there a force from the table or anything else other than the force of gravity, which is straight down. And in this case, you know, if there's air resistance, there'd be a force of air in that situation. Now, as this ball falls, you guys probably know as well as I do, it falls like this. It seems like it falls fast or slower in the beginning, and then in the end, it just seems to be falling really fast. So this parabolic path is the path of a projectile. So one thing to keep in mind here about all projectiles is this point. The horizontal component, so we know that horizontal is straight back and forward or left and right. It's just straight, exactly perpendicular to up and down. So that's what horizontal means. And then vertical is the other part of the projectile motion that we're going to talk a lot about today. It's not a very good line, but straight up and down, which is exactly perpendicular to the horizontal, is what we call vertical. Okay, so it says the horizontal component of a projectile's velocity is independent of the vertical component. So this is really important to understand what's happening mathematically. So in other words, what this is trying to say is it doesn't matter what's happening in the horizontal, it's completely unaffected by the vertical, which is kind of a big misconception that kids usually have with this. So I'm not sure how you're going to remember that, but as we have a projectile, whether it's, you know, up and down, or straight up, straight down, the idea is that if I kick it with a velocity in the horizontal direction bigger than a different kick that has, you know, a smaller horizontal direction, as long as my vertical is the same in both situations, I will have the same amount of time in the air. Because it doesn't matter how fast or slow I kick something horizontally, the time in the air has only to do with the vertical velocity. It seems simple, but it's a very hard thing to understand because every time you see a ball flying through the air, you see both the horizontal and the vertical happening on the object at the same time. But we have to believe, in order to get the math correct, and use the fact that the vertical and the horizontal, as long as they're at right angles to each other, act completely independent of each other in this projectile motion. Which I'm going to reiterate, it just means they are not affected by each other. Affected by the other. Okay, so it's very important to keep that in mind. Okay, well, I really like this picture here. It's one of my favorite ones on the internet because it shows a lot of situations. Just so you know, this is like a ball or a person. This green here is the vertical velocity. This X is the horizontal velocity. And that would be the same on each one of these pictures. The green, oh, I said X, but the purple is the horizontal. The green is the vertical. Keeping in mind, these things are independent of each other. So this note says that in the absence of air resistance, or in other words, fluid friction, the vertical component of a projectile's velocity will change every second, or actually every moment in time it'll change. Look at this. And this is shouting at you because it's all caps. Or not at you, at us. Acceleration due to gravity is always there and is always the same number and direction. Although the further away you get from a massive body like the Earth, you will have less and less gravity, but there is always gravity. And for us, what is that number? 10 meters per second squared. And we use negative because we say down is negative. That is always there. And if you understood what I said the first slide and believe it, what you want to know is that that affects only the y velocity, or the y part of the velocity. Notice, what do you notice about the x velocity? There's no acceleration on the x velocity. It's only on the y. And therefore, the y is continuously changing. So let's take a real close look at this here. So one of the reasons why I love this picture is that each ball placement is given at the same amount of time. So from where the ball is from here to here is the same amount of time as it is from here to here, which is the same amount of time as it is from here to here and here to here. Okay, my pictures aren't back very good, but these should be at the same level on this side as it is on this side, because like we studied extensively in last chapter and with the soccer ball punch, we know that going up is the same as going down in the vertical part of the projectile motion. Okay, but what do you notice here? Well, first of all, the distance from here to here is greater than the distance from here to here in the same amount of time. So, you know, that's a greater distance to fall in the same amount of time as this. This is less than that, and it starts getting really small there. And that'd be the same on this side too. So towards the top, there's less distance covered in the same amount of time as we get further and further down the line. So when we have less distance covered in the same amount of time, we're talking about velocity. Because remember, velocity is distance divided by time. And so if you look at the green arrows, you can see that's a bigger velocity than the one right before it, and that one's bigger than the one before it, and that one's getting to be very small, just like on the other side, but these are upwards because on the way up, this y velocity is slowing down, and on the way down, the y velocity is getting bigger. So look at these arrows here. If you remember anything about vectors, hopefully you remember that size matters, because the size of the arrow indicates the size of the number. So you can see velocity is getting smaller and smaller and smaller as you go up, and then larger, larger, and larger and larger as you go down. And these are all velocities in the y direction. Keep in mind that the y and the x are completely independent of each other. So what I'm talking about here is only the y velocity and how it is changing. Notice little g is always in this direction, right? Which means it's slowing it down on the way up because my velocity is in the opposite direction of little g, which means it's going to slow down, slow down, slow down, slow down. But then up here is where the velocity is in the same direction as little g, and therefore it gets bigger and bigger and bigger. So when your acceleration and velocity are in the same direction, your velocity increases. Okay, so we've been using this picture a lot, which is great. Another thing, though, that I want you to look at, because we're talking about the independence of the vertical velocity and the horizontal velocity. So what we're talking about is how these do not affect each other. So we talked about how the y velocity is changing on the way up and then changing on the way down. But really, now we want to talk about the horizontal velocity, because this says it never changes due to gravity. And the reason is because velocity in the horizontal is in that direction. Little g is completely perpendicular to it, which means there's going to be no acceleration or change in the velocity in the x direction due to little g, because that force of gravity is completely perpendicular of the x velocity. And this picture shows that. Does it look to you like this velocity is changing? Well, it shouldn't, unless the artist made a mistake. But all these velocity vectors are displaying the same size of the vector, which means it's the same number. So the velocity in the x direction does not change due to little g, or due to gravity, you could say. Very important. So we know the y changes, and now we can see that the x does not change. They're completely independent of each other. Okay, so now that we know that the horizontal is completely independent of the vertical, let's look at this a little closer. It says a projectile will have its minimum speed at the top of its path. And so if you look at the y velocity, we know that the x stays the same, right? So that part of the speed is the same no matter what. But the y velocity does keep changing and keeps getting smaller. And so the overall velocity becomes just velocity in the x direction, or just horizontal at the top of the flight. So you can see we're getting a smaller, 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 smaller y velocity until there's absolutely no vertical velocity for 1 instant. 1 instant, there's no vertical velocity. So when we did our soccer punt, right before it turned around, there it is. So right there, we've been using that a lot. That velocity in the y direction is 0, which only leaves then this horizontal component of the velocity for that 1 instant. So at the top of a path, the projectile will have its minimum speed. And why is that? Well, it's because there is no vertical velocity. Only left with the horizontal that never changes. So last chapter we talked about hang time. And it's kind of a good time to talk about hang time this year because the NBA Finals just is happening right now. In fact, the next game is tomorrow night. But hang time is always about just the vertical part of a jump. So if you look at this picture, knowing that each one of these ball positions is another or the same amount of time, the difference from each position is the same amount of time. Where do you see most of them? Right up here in the top. Okay, so it's kind of important to know that when you have this hang time, it's all about kind of the top of the projectile motion. And why is that? Well, because that's when it's the slowest overall. Because it's just x velocity. There's no y velocity here. In fact, most of these top positions, the y velocity is very, very small. And so it looks like you're just kind of hanging up in the air there. Keep in mind, little g is always forcing down on you the same way. A force of gravity causes a little g on your mass. So you are still accelerating with 10 constantly the whole way up and the whole way down. It just happens that at the top here, there's a lot more time because the velocities are so small at the top in the y direction. The velocities in the y direction are so small at the top. So the hang time is all about the top of the jump. So a lot of kids think that, so let's just say that you're, okay, so we want to talk a little bit more about hang time and how it has to do with track, okay? And more specifically, we're going to talk about long jump. So the long jump in track. Now the high jump is all about the y velocity, right? Because the higher y velocity you have, the higher you jump. But did you know that the long jump has a lot to do with the y too? So we're going to take a couple jumpers here. So this will be the picture for both jumpers. Okay, so this is the long jumper. And he's right at the edge of the board there. Okay, and he's going to take off and he's going to jump. Now notice this y velocity right here. So let's say that this, well, first of all, we got to make sure that our velocity in the x direction is constant. It's always going to be that much, okay, for this example. So the first jumper has a velocity in the y direction that I'll signify with green here. So when he takes off, he's going to have a y velocity that's that big, okay? And so his jump is going to be like this. Okay, now, here's the deal with him. The reason why he can go in the x velocity this far is because of the amount of time that he is in the air. Now I spell time with y because it's all about the y velocity. The bigger the y velocity, the more time in the air, the more your x velocity can act and get you a distance. Well, let's look at another jumper though. This guy jumps up, but let's just say he has a bigger y velocity, but he has this same x velocity. What do you guess is going to happen to his jump? Well, if he has a bigger y velocity, that means he's going to go higher in the y direction. And if he goes higher in the y direction, he has more time for your velocity in the x direction to work. And therefore, even though he's going the same speed in the x velocity, he gets more time to jump and move in the x displacement. Therefore, he has a longer long jump. Okay, instead of me boring you anymore, I decided that we would look at something a little more interesting having to do with projectiles. The note is the instant a ball is thrown horizontally, an identical ball is dropped at the same height, both balls will hit the ground at the same point. Now, here's the deal. A lot of people don't believe this is true. So, the famous Mythbusters, which I hope you guys still know who they are, they did a show on this. And these are the different pieces to the show. So there's 5 pieces here. It's a series. So you get to watch these 5 different pieces and then report back on if this actually happened and why it happened. Okay, hopefully you guys learned something. Have a great day.